Welcome to G Fun Facts Online. Let's start with a question. What if up to 75% of the sun's energy hitting a solar panel was being immediately locked away into an invisible state, a quantum dead end, where it eventually just bleeds away as useless heat? For decades, this wasn't a what if, it was a frustrating reality, a fundamental barrier limiting the efficiency of our technology. But what if we could find the key to that lockbox? What if we could harness this invisible energy? Scientists are now on the verge of doing just that, by learning to control a mysterious particle known as the dark exciton. To understand what a dark exciton is, we first need to talk about its sibling, the regular or bright exciton. Picture a semiconductor material, the heart of a solar panel, or an LED. When a photon of light strikes this material, its energy can kick an electron out of its comfortable position, leaving behind a positively charged empty space called an electron hole. Now, opposites attract. This negatively charged electron and the positively charged hole are drawn to each other, forming a temporary electrically neutral partnership. This bound pair is a quasi-particle called an exciton. You can think of it as a tiny, fleeting atom of pure energy existing for a brief moment inside the material. This is a bright exciton, and it's called bright for a good reason. After a very short time, usually just a few nanoseconds, the electron will fall back into the hole. When this happens, the energy of their brief partnership is released as a flash of light, another photon. This is the process that makes LEDs glow. In a solar cell, we try to pull the electron and hole apart before they can recombine, creating an electric current. So, bright excitons are the key players we can see and work with. But they have a hidden counterpart. Enter the dark exciton. Quantum mechanics has some very specific rules about how particles can behave, and one of the most important properties is called spin. You can imagine it like a tiny intrinsic magnet on the electron and the hole. In a bright exciton, the spins of the electron and the hole are oriented in opposite directions, or anti-parallel. This configuration allows them to recombine and release a photon. It's a quantum mechanically allowed transition. But in a dark exciton, the electron and hole have their spins aligned in the same direction, or parallel. This configuration is a forbidden transition. The laws of quantum mechanics forbid this pair from simply collapsing and emitting a photon of light. It can't interact with light directly. It's optically inactive. It's dark. For years, this was seen as a massive problem. In many of the most promising new materials, like quantum dots and atomically thin semiconductors, dark excitons are not just present, they are the overwhelming majority. For every one bright exciton formed, 3 or even more dark excitons can be created. This meant a huge chunk of the initial energy absorbed from light was being funneled into these dark states. And because they can't release their energy as light, they just wander around until they eventually transfer their energy to the material's atomic lattice, creating vibrations, which we feel as heat. In both solar cells and LEDs, this is a catastrophic loss of energy, a major source of inefficiency that scientists thought was unavoidable. But here's where the story takes a fascinating turn. The very property that made dark excitons a problem, their inability to release energy quickly, is now seen as their greatest strength. A bright exciton lives for mere nanoseconds before vanishing in a flash of light. A dark exciton, having no easy exit, can survive for microseconds or even longer. That's 1,000 times longer, an eternity on the quantum scale. Scientists realized that this long lifetime transforms the dark exciton from an energy sink into a potential energy reservoir. It's a stable, long-lived vessel for carrying energy. This shift in perspective is opening the door to technologies that were once considered science fiction. Let's talk about the most immediate application: solar power. The efficiency of a conventional single-junction solar cell is capped by something called the Shockley-Queisser limit, which puts the theoretical maximum at around 33%. A huge part of this limit is due to energy loss including the formation of those useless dark excitons. But now, researchers are developing methods for what they call dark energy harvesting. The idea is to not let that energy go to waste. Since a dark exciton lives for so long, it has time to move. It can travel through the material from where it was created to a specific defect or an interface layer that is engineered to interact with it. At this destination, one of two things can happen. The material can provide a little nudge, perhaps from thermal energy or an electric field, that flips the spin of one of the particles, converting the long-lived dark exciton back into a light-emitting bright exciton, which can then be harvested. Or, even more directly, the interface can be designed to split the dark exciton apart, pulling its electron and hole away from each other to generate electric current. Instead of losing 75% of these excitons to heat, we could start harvesting them. This would allow us to smash through the Shockley-Queisser limit, leading to dramatically more efficient solar panels that generate significantly more power from the same amount of sunlight. But the potential goes far beyond just better solar panels. It extends into the very language of information technology. In optoelectronics, the field that gave us fiber optics and LED displays, being able to convert dark excitons into bright ones means we can make LEDs that are far more efficient, wasting less energy as heat and producing more light. Now let's get even more futuristic and talk about quantum computing. The fundamental unit of a quantum computer is the qubit. Unlike a classical bit, which is just a 0 or a 1, a qubit can exist in a superposition of both states at once. To build a reliable quantum computer, you need qubits that are stable. They need to hold their delicate quantum state long enough for you to perform calculations. A bright exciton is a terrible candidate for a qubit. It's like trying to write a message on a firefly. It's gone in a flash. But a dark exciton? It's almost perfect. Its quantum state, defined by the spin of its electron and hole, is naturally protected from the outside world because it doesn't interact with light. Its microsecond-long lifetime is more than enough to encode and manipulate quantum information. Harnessing dark excitons, particularly in new atomically thin 2D materials, is a cornerstone of an emerging field called valleytronics. In these materials, electrons have an additional quantum property called a valley. By controlling which valley a dark exciton is in, we can encode yet another layer of information. This is like moving beyond a binary language of zeros and ones to something far richer and more complex, paving the way for revolutionary new forms of computing and data transfer. Of course, all of this hinges on one major challenge. How do you even study, let alone control, something that is defined by its invisibility? For decades, the existence of dark excitons was largely theoretical, inferred from the missing energy in experiments. But today, our tools are catching up to our theories. Scientists at places like the Okinawa Institute of Science and Technology in Japan have pioneered incredible techniques. Using something called time-resolved photoemission electron microscopy, or TRPM, they can essentially create ultra-high-speed movies of the quantum world. While they can't see the dark exciton with light, they can see its footprint. They can track the energy and momentum of electrons in the material and spot the unique signature left behind by a dark exciton, allowing them to directly observe its birth, its movement, and its eventual decay for the very first time. Other techniques involve using powerful magnetic fields to mix the properties of dark and bright excitons, temporarily making the dark ones visible so their properties can be measured. We are learning to map this hidden universe. The hunt for the dark exciton has taught us a profound lesson. Sometimes the greatest breakthroughs come not from looking at what is bright and obvious, but from developing the tools to track and understand the invisible. What was once dismissed as a flaw, an unavoidable energy leak, is now being revealed as a cornerstone for future technology. By illuminating this dark realm, we are paving the way for a new generation of hyper-efficient solar cells, advanced optoelectronics, and the quiet, enduring power of the quantum computer. Thank you for listening to G Fun Facts Online.